now that we have learned count vectorization in our previous chapter, we're going to talk about n-gram vectorization in this chapter. Hi, this is Shankar and welcome back to NLP with Python. So n-gram vectorization is pretty similar to count vectorization. In count vectorization, we treat each word, each individual unique word as a feature, and while creating the term document term matrix, and in n-gram we treat n adjacent words, all combinations of n adjacent words inside our file or inside a document as our features. And the formal definition goes as n-gram creates a document or matrix where counts still occupy the cell, but instead of representing single terms, they represent all combinations of n adjacent words. Right? So let's try to understand that with an example. And I'm gonna call this markdown, and let's suppose we have this sentence: I love NLP, or natural language processing. So if we try to create the features using count vectorization out of this sentence, it would be I love natural language and processing. These all would form our features, right? And with n-gram, we can define the collection of words or the number of words that should be taken into consideration, or the number of adjacent words that should be taken into consideration while forming the features. So if our n is 2, inside our n-gram, if our n is 2, the features would be I love natural language and language processing. So these would be our features inside our document or matrix, right? And the n can be anything. That the n can be something of our choice. And count vectorization is basically an n-gram where the n is 1, right? And let's try to understand how we can implement this in our code. So we are doing the same thing. We are trying to read in the data, and just for a reminder, we are dealing with this file which contains a list of messages which are classified as ham or spam, and we're trying to build a machine learning classifier or a machine learning model out of this file. And we are reading in the data using pandas library, and we are cleaning up the data. So in our previous chapter, when we were talking about count vectorization, we cleaned up the data, and we returned a list of words, or we returned a list of tokenized words after cleaning up the text or after cleaning up the data. And then we use the analyzer of the count vectorization, or we use an analyzer of count vectorizer to clean up the data and to create the feature or the document or matrix at the same time. But in this inside this method, we are not returning the list of tokens, or we are not returning the tokenized list of words. We are rather returning the complete sentence as it was. So what we are doing is we are removing the punctuations in the first line, then we are tokenizing the words, or tokenizing the sentence into a list of words, and then we are removing the stop words from our list of tokenized list of words, and then we are stemming the words inside a list of tokenized words, and we are joining them back using a space. So that would give us the complete sentence, right? Now let's run this method on our data set. So we are dealing with this data set which has these columns. So there's a column for level, and there's a column for text, and the labels would be either spam or ham, and the text would be the actual messages inside our file, right? So let's try to run this method using a lambda function on our data set, and try to create a new column inside a data set. So I'm gonna call that text underscore clean, and we are working with column text. So it would be dataset text dot apply, and let's say lambda x, and I would call the clean text method passing x, and let's try to print the first 5 records inside our dataset, and I would say dataset.head. So this is how our dataset looks. We have the label column, which is either a spam or a ham. We have the raw text, and we have the clean text. So the clean text is all small letters. We don't have capital letters, all lowercase, and we have the punctuation removed from here, and we have some of the stop words removed. We have the stop words removed from our clean text, and we also have the words stemmed down to their root words, right? Now let's try to apply the n-gram vectorization on our dataset. So n-gram is basically another form of count vectorizer, and if we just try to understand, count vectorization is actually an n-gram, which is where the value of n is 1. So we are considering each word, each individual unique word as the features, and we can keep increasing the value of n. So what I'm going to do is I'm going to use the same count vectorizer that I used in my previous chapter, and I'm going to try to build an n-gram model out of this. So I'm going to say n-gram vect equals count vectorizer, and I'm going to say n-gram range, and inside this we can actually mention the range. So if I'm saying 1, 2, that means all the single word, that is all the n equals to 1 gram and n equals to 2 gram words are going to be taken into account. So if we are saying n-gram underscore range equals 1, 2, that means all the unigrams and all the bigrams will be taken into consideration. If I'm saying 1, 2, 3, that means all the unigrams, all the bigrams, and all the trigrams are going to be taken into consideration. So we're going to keep one thing in mind. We might just want to play around with this value of with the range of n-gram that we can provide, but it's going to take a lot of memory if we make this range high. So what I'm going to do is I'm going to just say 2, 2. So this is going to take in the bigrams into account, and we're going to store our document tar matrix, or the cells inside a document tar matrix, inside x underscore counts, and I'm going to say n-gram vect dot fit transform, just like our previous video or our previous lesson, and we're going to call this fit transform on dataset, and we're going to call this fit transform on the text clean column of our dataset, right? So I'm going to say dataset text clean. So that's going to store the cells inside our document tar matrix into this variable x counts, and this is essentially a sparse matrix, and a sparse matrix is a matrix which contains a lot of zeros, and while storing, Python doesn't store the original matrix. What it does is it stores the non-zero characters, or the non-zero numbers, and the location inside the memory. So instead of storing the whole matrix, it just stores the location of the non-zero characters and the non-zero characters themselves, right? So this is going to hold the cells inside our document tar matrix, and we're going to create a data frame out of this. So what I'm going to say is x underscore counts underscore tf equals pd, so that stands for pandas. So that's the library that we have imported here, pandas as pd. dot data frame, and I'm gonna call this x underscore counts, and I'm gonna expand this. So this is stored as a compressed sparse matrix in Python, as I've already discussed. So I'm gonna call the toArray method to expand this. So that's gonna give us our data frame, and we're gonna name the columns inside our data frame. So I'm gonna say x counts underscore tf dot columns equals, we're gonna use the ngram vect, and we're gonna say get feature names. So that's gonna give the feature names for us, and that's gonna assign the feature names to the column names of this data frame, x counts underscore data frame, right? So let's try to run this. And one more thing I'm gonna do is print the first 5 rows inside our data frame. So I'm gonna say x counts df dot head, and let's try to run this. So this is how our data frame looks. So we can see we have the column names as inside our data frame as 2 words instead of 1 word that we were previously having for count vectorizer, right? Or count vectorization. So having a combination of words rather than having the individual words gives a bit more context to the words, and makes our model a bit more efficient in prediction. And that is how n-grams works, and that is all about n-grams. And in our next chapter, we're going to talk about TF-IDF, or turn frequency inverse document frequency vectorization. And stay tuned for the next one. Bye.